Okay, so hello everyone. Welcome to our new session of Yerevan Mathematics Colloquium. So today I'll be your host and I'm happy to present you our today's speaker, Levon Nurbekyan. So a short introduction about Levon maybe. So Levon is a long time friend of mine actually. We both started our undergraduate studies at Yerevan State University and then moved on to do PhD as part of the UT Austin and Portugal collab program. So there, Levon worked with Diogo Gomez and Alessio Figali from UT Austin side to do his PhD. And yeah, following his doctorate, he has held several positions as postdoctoral fellow and visiting positions also in McGill University and King Abdullah University in Saudi Arabia. And he's currently an assistant adjunct professor at UCLA and is working closely with Professor Stanley Osher and Wilfred Gangbo. So his research interests actually are quite similar to mine own. He has worked in nonlinear PDEs, in particular related to calculus variations and optimal control problems, but not limited to this. For example, he worked on problems on mean-field games, which I believe he presented in our last talk. And also a significant part of his research is related to optimal transportation problems. So he has a number of important contributions in these fields, in particular, and also their applications. So in particular, he has studied and developed connections between mean-field games and optimal transportation problems, and like these newly advances in such growing fields as neural networks and deep learning, and more generally in machine learning. So today we'll share his knowledge about these topics, and he will talk about leveraging the geometry of the optimal transportation, parameter identification, and related problems. So let's welcome Levon, and the floor is yours. You can start.
Thanks, Vartan, for the nice introduction, and also thanks to the organizers for inviting me. So yes, so I'll talk today a little bit about leveraging the geometry of optimal transportation in parameter identification and related problems. So more or less, I'll talk about two things. So one is the problem of parameter identification in dynamical systems, and the other one is the so-called natural gradient descent algorithm and PDE-based optimization. And both of these things, what we'll try to take advantage of, the geometry that optimal transportation theory provides. So let's start with a brief introduction on the optimal transportation theory. Who was, I believe, he was one of the scientists of during Napoleon times, and I think he had the task of remodeling the Versailles Castle, and then to do that, they actually had to, let's say, do some construction, then move the rubble from one place to another place. So, and if you have been in Versailles Castle, it's like a huge area. And if there are lots of things that you need to transport from one location to the other location, you want to save your efforts and you want to do it in as cheaply as possible. And so he formulated this problem formally and mathematically and did some advances there. But for a long time, there are critical theoretical aspects of the problem that were not clear how to address. And that's where a breakthrough came by the works of Leonid Kantorovich, who was a Soviet mathematician, applied mathematician, I would say. And so what he realized is that the original problem formulation of Monge can be actually reformulated as a linear programming problem. And once you do that, then many things become favorable in the sense that in the case of Monge, you could not, for example, prove in general existence of minimizer. The problem was highly nonlinear and so on. It was harder to study, but in the Kantorovich formulation, it was linear programming, and so you could prove existence of solutions and so on, and then you can go from there. And so the theory starts to develop rapidly after this. And so, in fact, Kantorovich, jointly with Koopmans, got a Nobel Prize in economics for his works on this, and essentially this was the invention of linear programming. And in fact, you should search on the web, on Wikipedia web page of Leonid Kantorovich. You can also find a CIA file on Kantorovich, which was found in the U.S. embassy in Tehran after the revolution. And so that tells us the importance of his figure and the research that he was quite a popular topic, and book already. So I mentioned a couple of ones. So one, which is the one that I learned from. So my first knowledge about open transportation was from this book by Cedric Diony. So the first one, it is a very nice introduction. It's based on his lecture note that he gave at Georgia Tech, and then he wrote another second edition, which is much larger, has more technical details and so on. But this first one is actually quite nice introduction. The books of different flavors. So there's computational optimal transport, where more computational aspects of this theory are studied. More, if you want more PDE flavor, then there is the book by Filippo Sant'Ambrogio. So it's open transport for applied mathematicians, and more abstract settings like metric space and so on. That's the book by Ambrosio, Gigli, and Savare, their application in economics and so on. So it's the literature is growing. And so, as I mentioned, there application economics, industrial engineering, analysis and probability theory, geometry, so imaging and graphic, and these two are popular nowadays: imaging and graphic, machine learning, and data science. Okay. Yeah. So let me quickly try to introduce a little bit what is the optimal transportation problem. So let's imagine that you have source points, which are drawn in blue color here. So, and let's say their locations are x1, x2. So let's first concentrate on the left half of the slide. So we have 2 points, source point x1, x2, and want to transport mass from this point to our target point, which are y1 and y2. And we'll assume that there is essentially conservation of mass. So no mass is created and no mass is lost when we're doing the transportation. So the incoming mass at every location should be exactly equal to the capacity of that location, and the outgoing mass from every source, the total outgoing mass from any source, should be equal to the capacity of that source. And so in this case, let's assume that I drew the point here proportional to the mass. And so let's assume that x1, x2, and y1, y2, they have exactly the same capacities. And I want to transport the mass from x1, x2 to y1, y2. And so there are 2 ways that I can do that without splitting the mass, right? So, and you can see that by the arrows, which are solid, and then dashed arrows. So there's 2 configurations of transporting, possibilities of transporting the mass from x1, x2 to y1, y2. if I do not split the mass, and in this case, if we assume that the cost of transporting the mass from between 2 points is, let's say, proportional to the distance between the 2 points, in this case, there is going to be no difference, and so all the transportation plans will have exactly the same cost. Now, you can have, of course, a slightly more complicated situation, which is the picture on the right, where, for example, you have that the Y1 has a larger mass, and then the source points also have different masses. So again, you want to match the incoming and outgoing masses, so there is no mass created or lost. So you want to do this in an optimal way. So there are two ways that we can formulate this problem. One, an analytic way on the continuum level, and another one on a discrete level, essentially the problem that is drawn here. So the discrete one is probably the simplest to explain, and essentially this is the mathematical setup, right? So I have source locations, x1, etc., xn, with capacities, a1, etc., an. So these are essentially weights. And I have target locations, there are endpoints, y1, etc., yn, and they have capacities, b1, etc., bn, which again represent mass. And so these are non-negative numbers that add up to 1. Now, let's assume that the cost of transporting a unit mass from a location xi to yj is given by a certain cost function, so t, xi, yj, and this t could be a distance or, it could be something else. So how do we formalize transportation mathematically? Well, we introduce a matrix, pi ij, which tells us how much mass we transport from location I to location j. And because I told you there is a conservation of mass, we have these two conditions. So the first one, if we look at all mass outgoing from a location I, so if we sum pi ij in the index j with the fixed I, then this has to be equal to the capacity of the location I, so it has to be equal to ai. And similarly, all the incoming mass to location j, which is equal to the sum of iij, where now it runs through the index I, but j is fixed, it has to be bj. And all of these entries have to be non-negative because, again, this is representing a mass that is being transported from location xi to yj. And so the optimal transportation problem in Kantorovic's formulation is as follows. So try to minimize pi according to subject to these constraints above, the total cost of transportation. So what is the total cost of transportation? Well, is the sum of cost of transportation from location I to location j. And for each ij, we transport mass iij, and we pay cost dxiyj per unit mass. And so that's the total cost. Okay, so this is a very nice formulation because it's amenable to mathematical analysis. In particular, convex analysis is extremely well equipped for studying these types of problems. And in fact, Kantorovich was approached by, I believe, a plywood factory that tried to optimize their processes, and this is a formulation that he invented and came up with. There is an excellent book. It's called Red 20 by Francis Spafford, which has the history of mathematical economics in Soviet Union, and in particular of Kantorovich's work, where you can read about this story. Anyway, this is the optimal transportation formulation in the discrete case, which can be written as a linear program. And so another advantage of that is that you can solve this numerically using linear programming algorithms. So there is, of course, another analytic formulation of the problem. And for that, let's assume that I have a certain initial measure, mu naught, and I have a target measure, reference measure mu naught, and I have a target measure mu1. And in the picture here, I assume that these measures are absolutely continuous, and this surfaces that are drawn are, for example, the graphs of the densities of this probability measure. And let's assume that I want to find now, instead of a transportation plan, a transportation map. Okay, so what is the difference? The difference is as follows. So in the transportation plan, I allowed the mass to split. So I could send part of the mass that is located at I to different J. But for now, let's assume that I cannot split the mass. So all the mass that is concentrated at some position X is being sent to some position P of X. And in that case, the mass conservation property can be written as follows. So mu1 of a certain set B. So if I have if I look at the subset of my target space B, and I compute all of the incoming mass, and how do I know what is the incoming mass? Well, that's the pre-image of that B through this mapping T. And since the sources had measured mu naught, then the total mass arriving at B is equal to mu naught of the mu naught image, the mu naught measure of the pre-image of T to B, and that has to be equal to the measure of B in mu1. So this means that the transportation is valid. So I really transport the measure mu naught to mu1, or in the language of open transportation or probability theory, you can say that mu naught is the push forward of mu1 is the push forward of the measure of mu naught through this mapping T. And I want to minimize the total transportation cost. And so you can see in this Mons formulation in the top is the integral over the original space, reference space X. So I transport all the mass from X to Tx, therefore I pay T as Tx, and of course the amount of the mass that is concentrated at the point is T mu naught X, and so this integral is the total cost of transportation through the map T. And so Mons formulation of this problem was as follows. Instead of searching for optimal transportation plan, search for an optimal transportation map. And you can see already that this formulation is nonlinear, because in general C is a nonlinear function in T, and also the constraint is nonlinear and hard to handle, of course, before it's a constraint. And in fact, it is an ill-posed problem from the mathematical perspective, because there are some cases where there are no maps. So imagine that mu naught is a delta measure concentrated at a certain point. Then, of course, any push forward, if I'm transporting it through just a map, then any push forward measure is going to be a delta measure. So I cannot transport mass from one location to, let's say, 2 or 3 locations if I do not split the mass. So problem number 1, that's why it's harder to study. And the analytic formulation of Kantorovich is given as follows. So now we replace, so we look at pi, which is a probability measure now on the product space, so that the marginals of pi are mu naught and mu1. So again, it's exactly the same condition that I wrote before, and it tells you that all of the outgoing mass from set A has to be equal to the measure or the mass that A has, and the incoming mass has to also agree. And so in this optimal transportation literature, we call mu naught source measure and mu1 the target measure. So there are a number of reasons why this optimal transportation is actually a nice mathematical construction, because it has connections with fluid dynamics and so on and so forth. And definitely one seminar might not be enough to cover all of these nice aspects and all of these applications. But maybe one thing that I would that is probably more relevant to the topic today is the distance that this optimal transportation generates. And so let's assume that the two spaces x and y are just the Euclidean spaces, and let's say p is some exponent, ph is equal to 1. And let's assume that the cost is given as the distance between x and y, the Euclidean distance between x and y, raised to the power p. So let's assume that that is the cost. And let's try to solve the optimal transportation problem with that cost. Then it turns out that the optimal value of this cost and normalized in such a way that the homogenized appropriately, so you need the power 1 over p. This WT function corresponding to mu naught and mu1, right? So if I take mu naught and mu1, I calculate the optimal transportation cost. I take the 1p of power of that. It turns out that WP provides a metric on the space of probability measures on the whole space RD that has a finite p momentum. Okay, so in a nutshell, the Wasserstein, so this distance is called Wasserstein distance or optimal transport distance, and it allows you to measure distances to measure how different are the probability measures. Okay, so it provides you distance on the space of probability measures, and if you're interested in like statistics or some machine learning applications and so on and so forth, where you need to compare two probability measures, you can use the Wasserstein distance to do that. So this is not the only possible distance. There are many others, but it has some nice properties. It has some nice geometric properties. So let me show you one example, so you get a flavor of what's going on. So let's assume for a moment that mu naught and mu1 are absolutely continuous, and I'll use the same notation for their density and the measure. And so we can look at two distances, right? So the Wasserstein distance, so W2, so I fix the exponent to be 2, W2 distance between mu naught and mu1. And I can also look at the Euclidean, so-called Euclidean distance at mu naught and mu1, because if, for example, the densities are square integrable, then I can embed these probability measures in the L2 space, and I can just look at the L2 error or the flat distance between mu naught and mu1. Okay, so this is a perfectly fine metric, right? And so let's see what are the geometries that these metrics give rise to, right? So let's suppose that I have two measures, and I'm interested in the geodesic connecting the two measures. And let's first concentrate on the left part of the picture. So I have let's concentrate on the top row. So I have a Gaussian concentrated at some location on the top leftmost image, and then on the top rightmost image is another Gaussian. And so let's say mu naught and mu1. And so what I see in between is actually the snapshots of the geodesic going from mu naught to mu1. Okay, so you see that if you go from left to right, you have so I believe you can prove that in the middle you always get a Gaussian, but even if that it wouldn't be true, you see that you have one bump. So mu naught and mu1 have one, they're unimodal, so they have one bump. And then in the middle, the interpolation also has one bump. So it preserves the structure of this probability distribution. In the second line, you have a similar situation where you have a 2D, I believe it's also a Gaussian concentrated in the top corner of the square, bottom left corner of the square, and then it's being transported to the top right corner, and you see again that the geodesic is actually preserving the unimodal structure of the probability measure. And you can also have fun and do this with arbitrary, let's say, images you can take an image and you can look at the pixel values, and you can think about it as a probability density function, normalize it appropriately, and then you can look at geodesic between, let's say, two different images, and you should search online, there are some found images. But here in this case, let's say we take a face and then another face, and then try to build a process and geodesic, which morphs one face to another face. And you see that this transformation is sort of seems very natural. So, okay, so now let's look at what's going on the right side. So in the right side, because we're just averaging, so the geodesic is just essentially, it's a linear space structure, so it's just a linear combination of the two things. So it's going to be a linear combination of the left and right things, and therefore you see that the support in the middle now is a combination of it consists of two disconnected sets. So in the middle you have two bumps interpolating with one bump function, right? And so therefore you kind of lose this nice structure. And you can see also in the second line, of course, again, it's linear combination of the densities, and so the supports will appear. And also in the faces, you see that still there is some, it is an interpolation, so there is some connection, but you see that on the edges there are some artifacts, and in general the reconstruction is worse than in the left case. And so one of the reasons why this happens is that if we go back and look at the definition of the vastness and distance, so let's look at, for example, like Monge's formulation. So you calculate the cost of moving from X to TX. So somehow it is important how much you pay for a so-called horizontal displacement. So if we're comparing two probability density functions, you pay attention to the horizontal displacement as well. Whereas if you're looking at the flat Euclidean distance, you're only interested in vertical displacement. So the change of the density at certain location. And in fact, many of these things can be, of course, proven. In particular, if you have that mu1 is just a translation of mu naught, then the vastness and distance will return you exactly the length of the translation vector. So it is sensitive to spatial displacement. And so if you care about applications where it is relevant, for example, morphing a face to another one, or there is some physical process morphing one state to another, these types of trying to use also transportation geometry might actually be a good idea. And so one of the goals in this type of problems is try to take advantage of this nice geometric structure and try to see whether one could actually leverage this geometric structure to solve some parameter identification problems, maybe some problems in machine learning and data science. And there are numerous success cases that I will not cover today. And one of the papers that I co-authored is Arnold, and I talked about this paper during the previous seminar, where essentially want to improve a machine learning algorithm by injecting optimal transportation geometry there. And also in some cases we might gain more theoretical insight on various problems. Okay, so let me start with the first application. And so the problem that we're interested in is actually, the formulation is actually very simple, but solving this problem in complete generality is actually challenging. So let's say you have some time homogeneous dynamical system. So x dot equals to Vx. And let's say we do not know what is this V. So typically V, of course, represents a physical law or certain update rules or whatever, right? So there is some dynamical system, but we don't know its form. So we don't know what is D, but we have observations from this dynamical system. And you can think about the times of Galileo, where he was doing all of his experiments with falling balls, and he didn't know what were the rules, but he had the carefully documented data, and he had observations. So the ball passed this location at this time, and then this location at this time, and so on. So, and he was trying to figure out what is essentially D. Right? It's a very old classical problem. Now, so typically in these kinds of problems, there are some parameters. So the velocity field has some parameters. Now, there are two cases. There are two ways the parameterization appears. So one is, let's say you have a certain physical model, and these parameters encode some unknowns in your physical model. So maybe you have some sort of a first principle or whatever, and you're trying to recover this velocity field, but there are some parameters that you don't know. One example, which is a quite popular example, it's called Lorentz 63 model, which was an attempt to model atmospheric dynamics, and after certain dimensional reduction steps, Lorentz came up with the following system of ODE. So it's just an ODE in three space dimensions, which has the following form, and there are three unknown parameters: sigma, r, beta, and these parameters, it's impossible to infer them, or at least it's not clear how to infer them from first principles. So these have to be found. And how do you find them? Well, you look at observations and you try to find these parameters so that they fit your observations as good as possible. So another approach is trying to find this D is, okay, we don't have any information about this D, so then we can try to build a mathematical approximation to find this D. And the parameter theta now play the roles of, let's say, expansion coefficients if we're trying to approximate D in a certain basis of polynomials, or polynomials for other functions. Or if you're trying to approximate, nowadays it's popular to try to build approximation using neural networks. There, the role of the parameters are played by the neural network weights and so on. So essentially, you come up with some approximation framework and then try to pick the parameters as best as you can. Okay, so yes, in either case, you want to find the parameters theta star that fit theta fast. And so what are the sort of the conventional or typical techniques of doing this? So typically your data, your observations are given as time series, and these are just snapshots of the state of your system at some times t0, t1, etc., tn. And again, if we think about the example of Galileo, where he was leaving the ball fall through the ramp, then maybe he was just recording the positions of the ball, let's say at certain times t1, t0, t1, etc., tn. Okay, so there are these observations, and let's assume that and what you want to do, you want to fit this trajectory. So essentially, you want to find the parameter theta so that x boldface x theta, which is the model, so the trajectory is corresponding to the choice of parameter theta, they're as close as possible to your observations x star. So you want to minimize the following thought. So it's some norm, some distance between x theta and x star. And typically, this is taken L2. It's just a nicer norm. Plus, there is some maybe regularization term r theta, and maybe, let's say, you want to find, let's say, expansion coefficients, but you want to have many coefficients to be equal to 0. So you want to find as sparse monad representation as possible. Then maybe you can use an L1 norm for theta, or maybe you just want your theta to be bounded, and so you can use the quadratic R. So it plays a role of a regularization. That's one approach. Second, you can try to fit the velocity, or on top of fitting the positions of the trajectory, you can also try to fit both. So, and then the velocities are given either by directly measuring the speed, so if it's possible, so if you can actually measure the speed, the time t0 equals to t1, or if it's not possible to measure the speed, maybe you can approximate the speed by certain finite difference scheme, so by observing the trajectories. And of course, in practice, both of the observations are noisy due to your equipment, or or maybe lack of information can be modeled as some sort of noise. Okay, so what are the difficulties in these types of problems? So some systems, and in particular Lorentz system, it is sensitive to they're sensitive to their initial conditions. And so, although we know that for short time we can actually, so let's say if the velocity is a Lipschitz constant, of course we can come up with estimates, stability estimates. So it's the distance between initial positions. We can estimate the distance between the so if we have two different initial positions and we track the trajectory, we can of course come up with an estimate between the distance in the two trajectories. But in general, if you look at the estimates, they grow exponentially, and in some case, you cannot do anything about that. So in the case of Lorentz system, you see that there are two trajectories, so the blue one and the red one. They start at positions that are very close to one another. So 10 and 10.001, and you see that after a while, these two trajectories become essentially independent. So there is no way, there's no estimate we can do about how close they are. So we start arbitrarily close, and then they diverge and essentially become independent. And for instance, you can see the evidence on the right-hand side where we calculate the L2 error between the two trajectories, and you see that okay, initially it's close. This is just this comes from the initial value problem, but then they start to diverge, and again, there's nothing you can do about it, and this is not a problem of numerical integration. This is just a mathematical fact. So another thing that could happen is that your sample, so the time that you sample might not be frequent enough so that you will be able to approximate the derivatives or the velocities using finite differences. So for finite differences to be accurate, you need small time intervals so that this approximation is accurate. And you see, for example, you can have many samples, like 10,000 samples. So these are just, you're recording where your data, where your points are, or you can have 10 samples. So it's very coarse. Then they're approximating using finite differences might be challenging. So then what you can do, you can change the perspective a little bit. So often chaotic systems, they admit well-defined statistical properties. So what does it mean? So it means that essentially what you can say is you can say something about the statistics of this dynamical system for a long time. So mathematically, if we consider this the following measure, which is called an occupation measure, and it basically tells you that in the time from 0 to capital T, on average, how much time the system spends at a certain location B. This is called the occupation area B. Now, you call rho a physical measure for this dynamical system if you have that the width limit of this rho xt measures is equal to this rho for a set of initial conditions that have a positive Lebesgue measure. Okay, so these are called physical measures. And so, in the spirit of statistical physics, instead of trying to fit the individual trajectory, what we can try to do, we can try to fit the physical measures, or it's like we can try to fit the long time behavior of our system. And so mathematically, you can write it as follows. So let's say rho theta is the physical measure produced by your dynamical system for the value of parameter theta, and rho star are the observations. So rho star, for example, could be this thing on the left, so the blue point cloud, or 10 samples probably will be not enough, but let's say, so you only have locations of these points. The time variable is suppressed, so only the long time information is preserved. So you can try to measure the distance between the physical measure produced for the value of the parameter theta and your data. Now, so then you need to come up with a notion of distance, and you want this distance to work in cases where, for example, these measures are singular, because for many of the dynamical systems, this is what's going to happen. So the physical measures will be singular measures, and so you want some distance that is able to deal with that kind of thing, and also you want it to be sensitive to geometric features, and you will see what I mean in a little bit. Okay. So so some of the advantages of changing this viewpoint is that now your system. So because for initial conditions, for many initial conditions, so for initial conditions with positive Lebesgue measures, you know that the physical measure, so the long-time behavior of your system, is going to be the same, and therefore you do not have the sensitivity with respect to the initial positions the way you had for the trajectory. So even if you have slow sampling, so this means that you cannot, you do not have time intervals short enough to approximate the relativity, still works. So as I mentioned, WP is well defined for singular measures. It reflects some of the geometric features, and the other sort of popular distances that you could use, even if in case when the distributions are actually absolutely continuous, they have some disadvantages. For example, if you have two measures that have translations of one another, and their supports are disjoint, then if you move around a little bit these two measures, the L2 distance or the L2 distance will not fit. It's going to be just constant because the supports are non-intersecting. Whereas WT distance will do that, and also the WT distance is robust to noise. So this is another advantageous property. So let me not go through this here, and I want to show you an example. So we have so let's first concentrate on the left picture. So the green trajectory is corresponds to two values of the parameter. So this is a Lorentz system, so the three-parameter family that I showed you. So the red trajectory corresponds to some initial guess of the parameter. So we do not know what are the parameters, and then optimizing the Wasserstein distance between the red trajectory and the green one. So we keep changing the parameters so that the trajectory that we produce matches the true trajectory as good as possible by essentially matching the long-time behavior or the measure. And once we do that, at the end, you see we get the blue trajectory that matches pretty well the green one. And you see that for going from red to blue, you really have to do a translation and also a little bit of scaling. And so this is not simply, comparing and adjusting vertical displacements. You need to displace, and you need sort of horizontal or spatial displacements to match it. And I did not talk too much about the noise types, but it works for this sort of intrinsic noise type. And you have a similar situation on the right-hand side where the data is given according to a different noise. Okay, so I don't think I'll be able to cover actually the second part in a timely manner. So I think I prefer to stop here, and maybe if there are some questions, we can discuss that. So I'll skip this second part because I was overly yeah. So I'll stop here because we won't be able to cover it in a nice way.
Okay. Thank you, Leon, for a nice talk. So now we can have some questions from the audience. If anyone has a question, please go on. Okay, so yeah, maybe if no one has questions, I can ask a question. So in this in these problems, I think so. You consider the like the distance between distribution of these trajectories, right?
Yeah.
Yeah.
So.
So I just wanted to understand if do you take into account like the time factor here, because so I believe there is this new, recently developed notion of causal optimal transportations. So basically it involves time factor there, so you don't want like you don't have information from the past of your trajectory in the future time. So, and this type of transformations take into account. So do you have something similar?
What was the name of the transportation that you mentioned?
I think it's called causal optimal transportation.
Oh, causal, yeah. No, so we didn't look at that. So in these things, we assume that that the time is suppressed, so we don't have like yeah. So we would not we assume that the time variable is suppressed here. Of course, for these things to be, I mean, one has to be very careful here, because dynamical systems, they can have actually very complicated behavior, and they can express these things which are called so essentially, you don't know a priori for how long you have to observe the system, so that you're sure that you have converted to the physical measure. So there is no where did they give? Yeah. So here you do not know what is this capital T, right? And so if you're observing a certain system, how do you know that the time has passed long enough so that you have converged? So you have seen all of the relevant long time behavior from your trajectories, because maybe there's going to be a long time where the system doesn't change much, but then after something they start to, let's say, go jump to a new part of your invariant measure and spend some time there. So it's a little bit tricky, and so you have to work under certain restrictive assumptions. But in general, yeah, these types of problems are difficult from that perspective.
Okay. Thank you. And maybe another question. So here you only consider dynamical systems, right? This type of coming from mechanics or physics. But do you think this type of approach can have applications in machine learning problems, where you have again parameterized system, but it's not a physical system, it's a model, or like neural network, or just some other models?
Yeah, people have been using these types of ideas for generative modeling, where let's say this is represented as let's say your data distribution, and you have some generative model. And so where is it? Okay. Yeah, so let's say you have some generative model that gives you distribution row theta, and then you want to match this with row star, and there are these things called W-GANs and stuff like that. So yes, people have tried to solve these types of problems for data science applications.
Do you know any specific applications of this?
W-GAN, for example.
Okay. Okay, so if nobody else has questions, so let's thank Levon once again for a nice talk.
Thank you very much for the invitation.